Hello and welcome back to another video. This video serves as the final video in this series. If you may remember, in the previous video we worked on the Craig-Nicholson method and plotted out the temperature profile for a bar over time, right? Now what we're going to do with today is perform a von Neumann stability analysis on that Craig-Nicholson method to illustrate that there are no limits on the time step on K or delta X, right? So with that being said, let's go ahead and get started. As you may see here on the whiteboard, I've already gone ahead and put our implicit differencing that we got from the previous video up. And then here to the right is our solution to our heat diffusion equation that we got previously. So we build in off these two things to illustrate that there is no time step variant or limit to our Craig-Nicholson method, right? So what we want to do here, and what you may recall what we did in the previous von Neumann stability analysis, is that we want to compare the temperature at a specific increment at the following time increment, how that relates to the temperature at that increment at the previous time step, right? What we want to do is illustrate that there is a constant or a variable out here, call it omega, and what we kind of want to achieve is to illustrate that omega has to be equal to or smaller than 1, right? Because that's what we determined was our issue in the previous method, that our omega was much greater than 1, and so in turn we had very high temperatures and extremely low negative temperatures, which were not possible for this situation. So we'll work this out and come to a conclusion to illustrate that constant or the variant, whatever, omega is equal to or less than 1, so that our analysis is more than stable. So with that being said, let's go ahead and get started. Like I said, we want to have the n plus 1 and n. So I'm going to take this out on the left hand side, make these all equal to it, and on the right hand side I'm going to pull out the Tj of n. Right? That being said, let's go ahead and get started. Right? So on the left hand side we said we're going to have Tj at n plus 1. Right? Then again, so the first term we look, we have negative z. And then what we have is j plus 1 compared to a j. If you recall what we did, we plug in a 1 for j, so we get ik delta x. That is the exponential for the first one, ik delta x. Then we have plus 1 plus 2z at the current one, so we just bring that coefficient out to the front, 1 plus 2z. Then we have a negative z, and this exponential is negative 1, so we're going to have a negative exponential to the power of ik delta x, and that's negative, right? Alright, so we got our left-hand side of the equation done with our tj n plus 1. Now it's time for our tj at time interval n, right? And so when we look, if you may notice, these two are very similar, and of course we're going to have a very similar expression to this. Of course, it starts off with j to the plus 1, so we're going to have z to the exponential power of ik delta x, and then we're going to have this coefficient constant, 1 minus 2z, and then finally this negative exponential, but there's a positive z, so plus z to the negative exponential of ik delta x. There we have it. Those are our two expressions in terms of the heat diffusion equation solution. And so, like we said before, we want to have Tj of n plus 1 and Tj of n in its own terms. So what I'm going to do here is bring this exponential over to the right hand side and divide it by this, or divide this by that, so that we end up with T of j at n plus 1 is equal to T of j at time interval n of this whole expression. Of course, we're going to have this in the numerator. ze ik delta x plus 1 minus 2z plus ze to negative ik delta x. Alright, that's our numerator, and as our denominator we have this. So we're just going to copy and paste that, right? Negative ze to ik delta x, and we have plus, what is it? 1 plus 2z, 1 plus 2z, and then we have a negative ze to the negative exponential of ik delta x. Alright, does that look correct? Let me double check. Z plus 1, 2z plus z. Alright, that looks good. So what I'm going to do here is actually erase this top part as we don't need it anymore, just to free up some space, and we'll continue from there. Alright. Give me a second. Erase this out. Alright, now we might seem a little stuck, but if you recall what we did in the previous von Neumann stability analysis, is we recalled Euler's equation or Euler's formula, right? If you may recall what it is, I'm going to write in terms of ik delta x just to simplify it. We get cosine of the component k delta x plus I sine of k delta x. Alright, of course we explained earlier, if we get a negative ik delta x, the only thing that happens is the sine to our sine switches, as it becomes cosine k delta x minus I sine k delta x. So with that being said, let's go ahead and integrate that for exponentials here and try to simplify it one step at a time. So of course we still have tj n plus 1 equal to tj n. Now we just simply want to multiply this out. So ze to the exponential will end up with z cosine k delta x plus I sine k delta x. However, you notice we also have a second z, and it's the negative. So what that will look like is plus z cosine k delta x minus zi sine k delta x. So what I'll do is that sine from here, we'll take away the sine from here, so that we'll end up with 2 cosine k delta x. So that's our numerator, 2 times z cosine k delta x. And of course we still have this plus 1 minus 2z. Alright. Make sure that's right. Our z becomes z cosine, and we add another one. Yes, that's correct. Now, same concept down here. We have, however, these are both negatives. So what this will look like is we'll have a negative z cosine k delta x minus iz, yes, because if this is all negative, then this all becomes negative. So negative z cosine minus zi sine k delta x. And then for here, what that will look like is we'll end up with a negative cosine, or negative z cosine k delta x. But in turn to having a negative exponential, the I sign becomes negative, and with the negative out front, it becomes positive, so it cancels out with this negative I sign here. So what we'll end up with is a negative 2 z cosine k delta x, and then of course this constant plus 1 plus 2z. Right? And of course I can go ahead and erase this stuff too again, just to free up some room. Alright, and then from here, what we can do is, like always, group our like terms, right? We see we have a 2z, 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 2z. So let's go ahead and group those together. Of course, we're still going to have this j n plus 1 equal to the j time interval n. And we're just simply going to group these. So we're going to pull this 1 to the out front, right? And then we're going to have a minus 2z. Then we'd have 1, right? Then minus cosine k delta x. Right? 1, and then we have minus 2z. 1 minus, yes, okay. And then we'll do the same thing for the denominator. Still have a 1. Then a negative 2z. I'm just going to do a positive 2z. And we have 1 minus cosine delta x. Alright, pull the 1 out front, minus 2z, we have 1 minus, because that becomes plus 2z, and then we have 1, yes, okay, that looks beautiful. Alright, now we can also, actually no, we'll leave it for now. Now, we're pretty much there. Of course, we have our j of n plus 1 and our tj of n on each corresponding side. However, we have these expressions. Now, what does this mean? I'm going to break this down a little bit. So, of course, we see we have a z in our numerator and a denominator. What does this see, right? Well, easy peasy. We would plug this in. This is equal to our alpha dt divided by 2 dx squared, right? That's our z. Nice and simple. Of course, these are all constants. These are all positive. Our alpha is positive when we plugged in, it was 1. Our delta t, which we're kind of changing, is also positive. And then our delta x, of course, is positive. So this whole expression is a positive, and we can keep it constant, right? But why is that specifically? Well, if we look at this cosine k delta x, like always, we've been talking about this a lot. What are the ranges for cosine? Well, cosine k delta x has to fall within 1 and negative 1, right? Can't be bigger than 1, can't be smaller than negative 1. Has to be between there. So if we look at that, how would that look necessarily? Well, if we have this 1 minus cosine delta k delta x, it has to be positive, right? As the greatest value it can be is a 1. So if we have a 1 minus 1, it'd have a 0. So we'd end up with 1 over 1. However, what I'm trying to imply here is that this cosine k delta x pretty much causes this whole expression to be positive, right? 1 minus a very small positive number or a very small negative number is going to produce a positive value, right? So what we can do from here is annotate this whole 2z 1 minus cosine k delta x as a variable, right? I'm just going to go ahead and call this omega, like we were saying earlier. However, this is not the omega yet. Plus 1 is equal to t of j comma n. So we'd have a 1 minus, like I said, this 1 minus cosine k delta x cannot be negative, right? So this 2z times this whole expression has to be a positive value. So say it's a w, omega, and then the same with this bottom, it is 1 plus omega, right? Now what does this mean? What does this mean? Well, like we said, omega can pretty much be any value, but it is here, right now. Omega is equal to 2z 1 minus cosine k delta x, right? And we know this is constant, or constant positive, because we know what z is. It's all positives. The alpha thermodiffusivity coefficient, then dx and dt are also positive. And if we're kind of messing with dt, our z and in turn our alpha or omega is varying, right? However, we came down to this final expression of 1 minus omega, which is 2z times that whole expression. And of course, 2z, like we just said, is full of positive values. And so what will that happen? Well, like I said, we have 1 minus omega in the numerator and 1 plus omega in the numerator. What does this mean? Well, no matter what value, pretty much no matter what value for omega, we'd end up with a greater denominator than a numerator, which shows that we'll never end up with a number greater than 1, right? Only in the instance of, actually, I'm going to free up some space up here so we can talk about this a little bit better. Very quickly. Yeah, I'm just going to rewrite this up here. Nice and big. Alright, so what exactly does this mean? Well, like I was just saying, there's pretty much no value for which this expression 1 minus omega over 1 plus omega is going to be greater than 1. Only in the instance where omega is exactly equal to 0, there we might have some issues where we get that 1 over 1, right? So that we get the temperature at the previous time, or the following time step, is equal to the temperature at the current time step. However, the key thing to notice here is that this expression 1 minus omega over 1 plus omega is never going to be greater than 1. That is because, simple math, 1 minus any number, plug in 1, 2, 3, whatever you want to get, or a very large number, or a very small number, we get with a greater denominator than a numerator, which gives us some kind of fraction or some kind of component to multiply the current temperature with. And therefore, this kind of proves that for z, this value here, which like I said is alpha times dt times step variant divided by 2 dx squared. Alright, this is constant, right? We have our alpha, which is 1 at the moment, and then our delta x is 1 at the moment as well. So whatever time step we plug in for delta t, this remains positive, this omega remains the same, remains omega, and this expression remains the same, where our denominator is bigger than our numerator, in turn giving us a value smaller than 1 whenever omega is not 0. And of course, we can do the same with dx if you want to be messing with that as well. We're not going to run into any issues if we vary dt and delta x however we want, as we have reached this Craig-Nicholson method. So with that being said and done, thank you guys very much for watching. I hope this was an interesting video to understand the analysis behind the Craig-Nicholson method. So thank you very much, and I'll see you guys in the next one.